Welcome back. So we defined what a general system was. Now let's go ahead and apply it to the problems that we'll see in robotics. Now there are many ways of defining a robot in robotics, and there's no real clear consensus on what a robot even is. For the purposes of this class, we'll go ahead with something that is perhaps more common than not. The idea that a robot is a machine that can sense, think or compute, and act. Now, this definition has a couple of keywords, so let's go ahead and start applying those keywords to build out our idea of the robotic space. In particular, the keywords that we're going to look at are the fact that the robot is a machine that has three characteristic functions: sensing, computation, and actuation. So, that first keyword, machine. The idea behind that is that this robot, this system that we'll call a robot, is a thing that we have engineered. It's a thing that we built. And so, we can come up with a dividing line between the things that we have built, that is our robot, and the things that we didn't build, that's our environment. So we can just go ahead and replace our environment, or represent our environment, with a system. So we'll draw a block. For the sake of convenience, we can label it E. And it's going to be an input-output system, just like we described. For right now, I'm going to draw it backwards, because what we really care about is the robot. Which means everything above this line is going to be the robot. Everything that we've built. Now, this robot needs to have three functionalities. It needs to sense, it needs to compute, and it needs to act. So we'll replace each one of those functionalities with its own subsystem. In order to sense, it's taking input from the environment. It's gathering information from the environment so that it can use it for the later stages of its operation. So we'll describe a system here, which we'll call our sensors. And that's going to interface with the environment. It's going to take as its input outputs from the environment and produce its own set of outputs. Its outputs will go into the computational block, the thing that does the thinking. Let's see. And that computational block, in turn, produces its own output that feeds into the actuation system. The actuators A, which then connect out into the environment. The output of the actuators are input into the environment to effect some change in the world. And so everything above this line is the robot. We can draw another line. Let's draw it right here, which is why I drew this in this particular way. Down here is everything that's tangible, that's real, that has some hardware interaction. The sensors, the actuators, they all deal with things in the real world, so they need to have some real presence. They need to be physical. Above this line, the computational block, not go below there. Of course, this computational block needs to be built on some hardware, but in this abstraction, in this system level breakdown, this is going to be mathematical or computational. It's going to be done in software, in code. With a short throwback to the 80s, we can say that this is going to be something that lives in the cyber realm. And so you'll often see robots referred to as cyber-physical systems. Basically, anything that has some amount of computation and some real-world presence will be a cyber-physical system, including robots. Now, there certainly are many interesting questions at this level or at this level, but in this class, we're mostly going to be focusing on the block up here, on the computational elements of the robotic system. Now, that's not to say that the rest of this doesn't matter. The problems that we will encounter stem from the interactions between the robot and the environment. And now that we have these systems, we can go ahead and describe some of the problems that we'll see in this class. So, the robotics problems that we'll find have to deal with a system-level breakdown. And so we can go and use that system mathematical abstraction and the terms that we developed to go ahead and really clarify what these problems are. And it turns out when we solve a problem, we're going to be given some information about the problem, our givens. And the objective, or what we're going to try to do in solving the problem, is to find some particular quantity. Now, another way of saying givens for a problem are inputs to the problem. And another way of saying what we're trying to find, the objectives for the problem, are outputs to the problem. So in a sense, we can think of these as additional systems. We're going to feed in some inputs, we're going to generate some outputs, and these systems are going to be the building blocks of our computational engine. So why don't you take a moment right now and think about various problems that you may consider when talking about robotics challenges. What are things that we may want robots to do that we'll need to break down into an input-output relationship? In particular, maybe using some of these elements of the overall environment, of the overall high-level system, along with the mathematical notation that we described for systems in general, how might we be able to describe inputs and outputs to characterize a set of problems that we may face? Why don't you pause this video for a moment and write down a list of problems that you may think of, as well as an input-output description of these problems. Take a moment and do that, and then come back and join us. Okay, so we're going to list a bunch of givens, a bunch of things that we know about our overall system, and what we don't know, what we're trying to figure out in order to solve a particular problem. So, what are things that we can do? Let's say we know the physical systems, everything related to here. We have a known piece of hardware. We have a Roomba or a self-driving car or a selfie drone. We know our system. So our given is a system. Our system is characterized by F and H, the system dynamics and the output equations. If we know our system, we may want to get our system to solve a problem. That is, we're also given some task objective. Now, how might we describe a task objective? We may say that given a particular system, our robot, we want a robot to do something to the environment. That is, we want our robot to have a particular output. If we know our system, and we know the output that we want our system to have, one question we may ask ourselves is, what is the state that we need within our system that can accomplish that set of outputs? Keeping in mind that each quantity, each signal within our world is a time signal, we can say our objective is to find a state trajectory x. The sequence of states that, when executed, will generate the appropriate objective. We're going to call this our planning problem. Now, one thing to note, here I've noted that our task objective is defined by a sequence of outputs z. In practice, we may find other ways of describing our task objective, perhaps not in terms of z, but in terms of additional quantities, that we may eventually be able to resolve down to a z, or we may not even really worry about that. In this case, I'm writing this as a general proxy for some mathematical quantity that defines our objective. If we have that, plus complete knowledge of our system, we may want to figure out what the sequence of states is that will generate this. Now, for a specific instance of a problem, we'll be given the information, and we'll compute a specific set of numbers. First go in state x1, and then in x2, and x3 for all time. What we're trying to come up with in this class is this system block, is an algorithm that solves the planning problem generally. That given any definition of the planning problem, we can apply this technology, the tools, for the algorithms for doing planning, and generate a trajectory. So our goal in this class is not to find a specific trajectory. Our goal is to find a planning process that somebody else can use to find a trajectory for their robotics problem. Now, very similarly or very closely tied to the planning problem is the question of, if we know our system, again, which is our f and our h, and now we know our trajectory, our state trajectory x, how do we execute that? How do we implement that? How do we define our inputs, u, that will get us to follow this trajectory? That's known as the control problem. And I say these are closely tied because the planning problem is trying to get us to solve some task. It doesn't really help us in solving a task if we come up with a trajectory for which we cannot define a set of inputs to accomplish that trajectory. So oftentimes, these two problems will be connected. Our goal is to solve some objective and determine the set of inputs that accomplishes that objective directly. And we'll need to go through the system, we'll need to go through the states, but in practice it's one big problem. Sometimes we will be able to break it down into two separate processes, two separate systems, to take us from one to the next. Sometimes we'll go ahead and connect them. And like most things that we'll come across in this class, that's not a universal consensus. This breakdown between what constitutes planning and what constitutes control is again a matter of opinion. I've found that this particular breakdown is often the best way of describing it. In practice, you will often not see one problem in isolation of the other. In robotics challenges, we'll need to do both planning and control. Now, for both of these, or for the planning and control problem, we start with this notion of the task objective. The reason we apply this, or the reason that in one case we can define a task objective as a sequence z, as the output to our robot, is that the outputs to our robot feed into the environmental system. But if we have an input to our environmental system, and our environmental system is a stateful system, there may be some state involved in the environment. And in fact, our task may consist of trying to define the state of the environment rather than just trying to define the outputs to our robot. And in that case, we may need to know what the state of that environment is. But as we described, the state is an invented quantity. It's something that we made up to just let us have a mathematical description of the entirety of this block. Which means if we're going to be doing math with it, we need to know its value. Up here, in our computational system, this is us. We live up here. We have access to everything inside here. If we define a state, we can just look at that memory value and figure out what that state is. But anything down here in the physical world, it may have a state that is not directly accessible. All our computational engine knows is the information that's coming across these arrows, the inputs into our system. And so, let's say we have a system. In this case, we're not talking about the robot system, but we're talking about some other system. It may be a part of the robot, maybe some hardware robot system. It may be the environmental system. Regardless, we have some system. And for this system, we're able to observe all of the physical quantities related to it. So we can see what's going into that system, maybe because we generated those quantities ourselves. We can see what's coming out of the system, maybe because that's coming into our system as well. So we have our inputs and our outputs to that particular system, which is U and Z. Given all of these, we want to figure out what is the state of that system itself. This is known as state estimation. In this class, we will consider it comparable to the question of perception. Again, similar to the breakdown between planning and control, the distinction between state estimation and perception is again a matter of opinion. In this class, we won't really worry about that too much. So the goal of state estimation is to figure out the actual quantity that relates to this made-up value of the state. Now, there's a little bit of a distinction between the state estimation problem and the planning and control problem. In the planning and control problem, we're talking about the system that we have, that we're talking about. When I say we, I refer to our brains being the thinking, the computational part of the robot. We know everything about it, and we're just trying to say, what would be a good trajectory to do? What would be a good way of implementing or executing on that trajectory? How can we do this given ourselves? In the state estimation perception problem, we are looking at a different system. So rather than these being the system not thinking about itself, the system will be thinking about some other system. The computational system will be thinking about, let's say, the environment or some other hardware-related systems. Okay. Now, they're going to be, these are going to be the main questions, the main problems that we'll be looking at in this class. There are a few additional questions that will show up over the course of this material. We'll go ahead and, again, write it down in this form. There's been a very classical problem that has existed before robotics was called robotics, and maybe was known by the term mechatronics, or generally engineering. What if we don't actually know the exact system that we're querying? So similar to the state estimation perception problem, where we're talking about evaluating a different system, but now instead of having a fully known system, we have a partially known system. I say partially known. It could also be a fully unknown system, but in practice it becomes very hard to deal with complete uncertainties. Maybe the partial thing that we know is the structure of f and h. We know that f and h are linear, or we know that they're quadratic. We know something about f and h, but we don't know the specifics. We don't know the details. What we can do is, once again, we can observe all the physical quantities, the inputs and outputs to that system, u and z. And the goal is to actually figure out what is going on with that system. Come up with the specific mathematical formulation, specific mathematical functions that relate to f and h of this partially known system. This is known as system identification, or sys-ID. Also modeling. Depending on which side of the pond you are, there's either one L or two L's in there. I don't remember which one's which. We're not going to cover this in this class, but you may need to do this in order to then take this information and throw it into one of these additional problems. For most of the stuff we'll do in this class, we'll be given the actual functional relationships of the system, so we don't need to worry about system identification or sys-ID. Now, there's one final problem that I'd like to bring up, and now we're going into a higher level of abstraction. We have all of these problems. When we have these problems, we're going to want to come up with a solution for them. These are all assuming that the system is fixed. Either it's fixed and we know what it is, or it's fixed and we don't know what it is, but we can find out. We may have the ability to design our own system from the ground up. We can choose to build our own self-driving car rather than buying one from any well-known company. Or we can go ahead and actually buy raw components and build our own selfie drone, or whatever other robot that we need to accomplish our task. So in this case, we still start with the task objective, and maybe we can determine it or define it in terms of some outputs that we want our system to produce. We can maybe define it in terms of some state that we want to affect within the environment. There may be other quantities that we can throw in to defining a task objective, similar to what we did up here. But now in this case, once we have our task objective, our goal is to find some system, find some f and h function that meets some criteria that perhaps makes the planning and controls problem easier. Perhaps it makes the manufacturing of this level cheaper. Perhaps it makes the end result, the quality of the objective, higher performance. Whatever we can throw into our task objective, our goal may be to define the system itself. And this is going to be the question of design. Now, for these problems up here, we're going to come up with systems in here. We're going to come up with algorithms, mathematical tools that can take inputs and generate outputs. Historically, solving the design problem involved having a system in here that consisted of an engineer. One of you guys. You get presented with the task objective, and based on your entire time history of inputs that involves learning and doing and reading and watching, you go ahead and manually create your system. You go ahead and create a system that solves this problem. In fact, you may end up doing that as a career once you're done with this class. But it doesn't need to be there. Recently, there's been a lot of developments on removing the human from this process, from this system. And just like all these other systems that are computational tools, can we go ahead and come up with computational design tools that can find some way of generating a particular system design based on objectives. So this is an area that I'm particularly interested in, and a lot of my group and a lot of my research revolves around filling in this box. There's many ways of doing it, and it's still a very open challenge. Hopefully we'll be able to get into some of this material, and hopefully you guys will go ahead and create some of the tools that fit into here that expand the capabilities of robotic creation in such a way that then we are no longer limited by the little human inside the box and are able to create much better solutions with much better outcomes. Okay, so these are the problems we're going to look at, and we'll go ahead and get started up here with the questions of planning and control next week. But before we wrap up for this week, I want to take a quick detour and talk a little bit more specifically about the concept of state. As we saw, we broke up our mathematical framework depending on whether the state was discrete or continuous. The state itself has a lot of impact in the problems that we will be addressing. And so it's worth going into it a little bit more detail and perhaps giving some examples that we'll see a lot in the world of robotics. But before we get into that, let's go ahead and take a quick break. Maybe grab yourself a snack, you deserve it. Keep your blood sugar up and then come back and we'll wrap this up with a brief exploration into state.